Good day to us all, ladies and gentlemen. Today we'll be looking at how lines and vectors are very, very interrelated. So I have an orange line drawn on my canvas here. And I'm going to put another point on here. Let's call it point R. So this is line AR. So how is this related to vectors? Well, that line is going a certain direction, right? So really, we should be talking about the direction vector B. This line is parallel to that direction vector. We have vector R here. R is equal to vector OR, remember. And to get vector OR out of this, we would take vector OA and add to it AR. Yes? Is that familiar to us from our introduction to vectors? R is the resultant from adding OA and vector AR. And wherever I put point R on this line, we would get this vector equation just like this. And we know that AR is parallel to some direction vector B. And if you remember, things that are parallel will be scalar multiples of each other. Vector AR is a scalar multiple of vector B. So R can also be given in the form vector A, I call this blue vector, vector A, plus some scalar multiple, I'll call it T times vector B. This is the equation for a line using vectors. And the way we can think about it is we have our R vector, this red one. We can make any length vector we want by taking some point on the line, if you will, plus some multiple of the direction vector. And if we take a whole bunch of those direction vectors together and stack them on top of each other, going opposite directions, so positive and negative t values, we get this line. Okay, cool. So let's go into using this information to write equations and solve problems involving lines. Before we do, it is important to note that there are three types of lines when we're in three dimensions. There are coincident lines, and we should know what that is from our Algebra 1 time. They're lines that are really the same line. It's one directly on top of each other. They're exactly the same. They're parallel. Parallel lines will have direction vectors that are scalar multiples. But they don't intersect each other. And the last type is skew lines. And skew lines never intersect. So, up in this diagram, skew is a little bit more difficult to envision, but if I were to take line HE and line GD, those two never intersect each other, but they're also not parallel. They're going different directions. So they're different direction lines, but they never ever intersect each other. And that's kind of a different idea than we experience in two dimensions. We couldn't have this. The lines were either the same line, they were parallel, or they had to intersect each other. And with vectors, that doesn't have to be the case. We can have lines that are not parallel, but also that don't intersect. All right, let's write a couple vector equations. I want you to pause the video and see if you can write down an equation for part A. All right, so it's a vector equation, ladies and gentlemen, which means we do need something equals. I'll call it R equals. A lot of times we use vector R to mean line, but you don't have to. You could use L if you wanted. We're going to take a point as a vector. So that's my OA. This would be my A point, if you will, from the last slide. Plus a parameter, t, a scalar multiple, times a direction vector. And there we go. There is my equation for this line passing through the point 1, negative 1, 3, and parallel to that direction vector. For part B, what's different? Well, they don't tell me the direction, but we can find it. The direction vector is going to be vector AB, or for that matter, we could find vector BA. It does not matter which direction you go between these 2 points, because we're going to be multiplying by a scalar which can take both positive and negative values. But vector AB, I'm going to take my terminal point minus my emanating, so negative 2 minus 1, 1 minus 0, and negative 1 minus negative 4, which is 3. Now I have enough information to write my equation. I'm going to use a different letter for this equation. I'll call it L. Can't call them both R, otherwise we're saying that they're the same. So we need a point, and it doesn't matter whether we use point A or point B. It goes through both of them. I'm going to use A. Plus some parameter, different parameter than the first line, times the direction vector. And there we go. There is my equation for the second line. Now, here's the next wrinkle. These two lines, I'm going to tell you, they intersect each other. And I want to know what the angle between these lines is going to be. And we're going to look at the acute angle almost always. When two lines intersect, there's almost always an acute angle and an obtuse angle. When we do this, we're always talking about the acute one unless it specifies find the other one. So here we go. I'm going to use my dot product to find this angle. That's what we use dot product for, after all. We found that the cosine of theta, the angle in between, is equal to the dot product, so L dot R, divided by the magnitude of each, multiplied together. So the dot product here is 3. The two magnitudes are square root 11 and square root 19. So the angle is going to be the inverse cosine of that stuff. And I'm going to type this into my calculator. It's 3 divided by 1 square root, where I'm doing 11 times 19 inside of it. And what you should end up with doing this calculation in degrees is 78.0 degrees. Second and final example, we have two lines called R1 and R2. We want to show that these lines do indeed intersect, and I want to find the point where they do intersect. And the way we're going to do this is we are going to solve a system of equations. We're going to write what are called parametric equations. And what those are going to look like is we're writing the component for each one of these things. So for vector R1, the x piece is 3 plus 1s. The y component of vector R will be 0 plus 1s, and the z is going to be negative 1 plus 1s. These are the parametric equations for line R1. And they're called parametric equations because they depend, the point that we're going to get on that line depends on the parameter s in this case. Pause the video and write down your parametric equations for line R2. If you're really doing well, you found the parametric equations for R2D2. Get it? Star Wars, I'm funny. We're moving on. For R2, we get x equals 6 plus 0t. For y, we get 2 plus 6t. And for z, we get 0 plus 8t. So let's clean up a few of these. For R1, y is really just s. And for R2, x is 6, and for z, well, z is just 8t. So we have a system to solve here. And what we're going to do is we're going to equate all of the x, y's, and z's, because if these two lines are going to intersect, they're going to share an x, y, z ordered triple. So we can write 3 plus s equals 6. That's my x equation. S equals 2 plus 6t. And negative 1 plus s is equal to 8t. And what's going to happen here is we're going to take two equations and we're going to solve those two equations for the two parameters. And then we're going to make sure that they work in the third one. And from the first equation, we can see that, well, this one I don't have to do elimination. I know right here that s is equal to 3. And then I can substitute that into the second equation and get 3 equals 2 plus 6t. Subtract 2, we get 1 equals 6t. So t is equal to 1/6. Now to find out if these two things do indeed intersect each other, we're going to take our value of s and our value of t and substitute into that third equation for z. And we're going to get negative 1 plus 3 equals 8 times 1/6. We get 2 equals 4/3. What? 2 doesn't equal 4/3, so it's okay. What this means is that these two lines do not intersect each other. If they did intersect each other, we would get a statement of equality right here. But they don't, and that's okay. So, can I find the point of intersection? No. But let's talk about how we would anyways. We would take these two values for s and t, and we're going to take the value of s, and we're going to substitute it there. And we'll get an ordered triple. We'll do negative 3 plus 3 times 1, 0 plus 3 times 1, negative 1 plus 3 times 1, and we'll get an ordered triple. And then, to make sure we haven't made any mistakes, we're going to take the t value, substitute it there, and make sure that we get the same point. So the question arises, since these lines don't intersect each other, are they parallel or are they skew? And to tell that, we have to look at the directions. The direction of R1 is 1, 1, 1. The direction of R2 is 0, 6, 8. Are these direction vectors parallel to each other? And we can safely say, no, these direction vectors are not parallel to each other. And you're saying, how do you know that, Mr. Schnack? Well, they're not scalar multiples of each other. And that, ladies and gentlemen, is where I leave you on this glorious day. Have fun writing equations for lines using vectors.